Hey everyone, welcome back. So today we're going to dive into a super important chapter in your physics syllabus. Yep, it's electricity and magnetism. Look, whether you're here for some last-minute revision before your exam or you're just starting this topic, no worries, I got you covered. We're going to go from the simple sparks you see all the way to how the wiring in your house actually works. Sounds good? Jump. Let's get started. All right, let's kick things off with a little brain teaser. Think about this for a second. What could a massive flash of lightning in the sky possibly have in common with an electric eel that can give a crazy 600-volt shock? I mean, they seem totally different, right? One's in the sky, one's in the water. So what's the connection? And the answer is static electricity. Can you believe it? Both of these incredible, powerful things run on what we call electrostatics. And really, all that means is electric charges that are static, not moving around. It's the science behind pretty much every spark, shock, and zap you can think of. Okay, so for our first part, we're diving deep into this power of a spark. We're going to break down exactly how these static charges build up. And you know what? It all starts with something as simple as rubbing things together, friction, and these tiny little particles called electrons doing their thing. So imagine this. You rub a balloon on your hair, right? What's actually happening is that tiny electrons are jumping from your hair to the balloon. Now, this is super, super important to remember for your exams, okay? Only the negative electrons can move. The positive protons, they're stuck. They cannot move. So it's pretty straightforward. The thing that gets extra electrons becomes negative, and the thing that loses them becomes positive. Simple as that, la. And once these objects have a charge, they follow one simple golden rule. It's like this. If the charges are the same, so positive and positive, or negative and negative, they will push each other away. They repel. But if the charges are opposites, one positive, one negative, they attract each other. They pull together. And believe it or not, this one single rule explains so much stuff, like why dust magically sticks to your TV screen, and even how lightning works. Right. Let's use lightning as a huge example. Just follow the steps here. First, you've got clouds moving around, rubbing against the air. This friction causes a massive buildup of static charge. Then, as you see in step 2, the bottom of the cloud gets all negatively charged. And what do opposite charges do? They attract. So this negative charge in the cloud attracts positive charges on the Earth's surface. You get this massive pull between the cloud and the ground. And eventually, that attraction gets so strong that zap, a giant spark jumps across. And that, my friends, is lightning. All right. We've talked a lot about charges that just sit there, static charges. But what happens when they start to move? Well, that's when we get what's called an electric current. And to really get a grip on current, you need to know about the big three that control everything. We're talking current, voltage, and resistance. First up, we have current. We use the letter I for it. Now, don't overthink it. Current is just the rate of flow. It's how many charges are zooming past a certain point every single second. The best way to imagine this? Think of a water pipe. A high current is like a huge amount of water gushing through that pipe really fast. Okay, so what makes the charges move in the first place? That would be voltage, which we call V. Voltage is the push or the pressure behind the flow. Your textbook might call it potential difference, which is the proper term, but just think of it as the push. Going back to our water pipe, voltage is like the pump that creates the water pressure. The more pressure, the stronger the push and the faster the water flows. And the last of the big three is resistance, or R. Now, resistance does exactly what it sounds like. It resists the flow. It's anything that tries to slow down the current. It's the obstacle. So in our water pipe analogy, what would resistance be? It'd be like a really narrow part of the pipe, or maybe some gunk inside, that makes it harder for the water to squeeze through. And just remember, basically every electrical component has some amount of resistance. Okay, so we have voltage, the push, current, the flow, and resistance, the obstacle. But how do they all connect? Well, they're all linked by one incredibly important formula. And I mean it. This is probably one of the most important things you'll learn in this chapter. It's called Ohm's Law. Seriously, you need to tattoo this in your brain, because I can guarantee you, 100%, this will come out in your exams. And there it is. So simple, right? V equals I times R. That's it. Voltage is equal to the current multiplied by the resistance. This little formula is the absolute key to everything. It shows you the exact relationship between the three. So in an exam question, if they give you any two of these values, you can always find the third one using this.
It's your secret weapon for solving circuit problems.
Now, before we start calculating, we need to know the language of circuits, the units. This table is basically your cheat sheet, so pay close attention. Voltage, we measure that in volts, symbol V. Current is measured in amperes, or we just call it amps, symbol A. And resistance is measured in ohms, and it has this cool Greek symbol omega. You must know these units and their symbols for your calculations, okay? Okay, so we've got the formula, we've got the units. What's next? Well, let's put it all together and see how it works in the real world. We're going to look at the two main ways you can build a circuit. We call them series and parallel circuits. Okay, check this out. This slide lays out the difference perfectly. On the left, you've got a series circuit. See how everything is connected in one single continuous loop? The current only has one path to take. So what happens if one bulb blows? Poof, the whole circuit breaks and everything goes off. It's a disaster. But now, look at the parallel circuit on the right. The current has choices. It has multiple paths it can take. So if one bulb here decides to give up, no big deal. The current just takes the other paths and the other bulbs stay lit. See the difference? So this leads to a really practical question. Think about your own house. You can turn on the TV in the living room without having to turn on the light in your bedroom, right? And when one light bulb in the kitchen burns out, the whole house doesn't suddenly go dark, does it? So why is that? Which type of circuit do you think we use at home? You guessed it, our homes are wired in parallel. And there's some very, very good reasons for this. First, it means every single appliance, from your phone charger to your fridge, gets the same full voltage from the mains. Second, you can switch everything on and off independently. And third, and this is probably the most important thing, it's reliable. Imagine if your whole house went dark just because your toaster broke. That would be terrible, right? Parallel circuits prevent that. All right, for our last section, we're going to look at something really cool. It turns out electricity has a secret best friend, and that friend is magnetism. Here's the mind-blowing part. Whenever you have an electric current flowing through a wire, it actually creates an invisible magnetic field all around it. This amazing link between electricity and magnetism is called, you guessed it, electromagnetism. So we can actually use this effect to build our own magnet called an electromagnet. All you do is take a wire, coil it up, and pass a current through it. Boom, you've got a magnet. But here's the magic trick. It's a temporary magnet. The second you turn the current off, the magnetism completely disappears. This ability to switch it on and off is what makes electromagnets so unbelievably useful. Okay, but this magnetic field is invisible, right? So how do we know which way it's pointing? Well, there's a super easy trick for that, called the right-hand grip rule. You can even do it with me right now. Take your right hand, okay? Pretend you're grabbing the wire. Now, point your thumb in the direction the current is flowing. See how your other fingers curl around the wire? That's it. The direction your fingers are curling is the direction of the magnetic field. Super useful, right? So what if we need a really, really strong electromagnet? How do we power it up? Well, this chart here shows two very simple ways. First, you can just increase the current. More current, stronger magnetic field. Easy. The second way is to add more turns to the coil of wire. The more loops you have, the stronger the magnet gets. It's as simple as that. And trust me, these powerful, switchable magnets are absolutely everywhere. We're talking about those massive cranes in junkyards that can lift entire cars. They just switch on the electromagnet to pick it up and switch it off to drop it. They're also inside electric bells, the magnetic locks on doors, and get this, even that little magnetic strip on your debit or credit card uses this technology to store your information. Amazing, isn't it? So there you have it. We've gone from a tiny little spark all the way to these massive invisible forces that can lift cars and store data. It's incredible stuff. So I'll leave you with one final thought to ponder. We're already doing all this with electromagnetism. What do you think is the next huge problem this amazing science is going to help us solve? Think about it. Thanks so much for tuning in, and all the very best with your studies.